Hi, everyone. Happy to be here. So one quick word ahead about our company, Monolith AI. We've always been about, so Paul, for instance, at the beginning has told us amazing stuff about how machine learning is working in autonomous driving. Our focus from the start has been, have a look at how amazing autonomous driving is. Wouldn't it be great if we can get some of those technologies into the research and development process as well? And so Monolith is a machine learning platform to accelerate decision-making in R&D. Today, what I wanted to do is talk about one specific use case where we were lucky enough to recently get real data. And the use case, as you can hopefully see in the video that is currently playing, is about track testing. It's about the fact that you have to do a lot of different track tests in different scenarios, whether that's in the Sahara Desert or in the north of Norway, in wet conditions or in high-speed conditions. You need to do a lot of different tests. It costs quite a bit of money and it takes quite a bit of time. And seeing that machine learning can recognize complex scenarios, we were thinking, can we build a tool that helps test engineers to reduce the amount of time they need to spend on the test? And this is a case study I'm particularly excited about because we had a partnership with Kistler. It's a German-Swiss 500 million company that specializes in test equipment. And they were so generous that they've made the entire case study, including all of the track and test data, fully public. So if you're interested in this and if you're interested in the results, this is a case study where you really don't need to take my word for it. You can log into a free trial of Monolith after this and have a look at the data yourself and have a look at how we managed to reduce the amount of test time by 70%. Using machine learning together with a team of automotive engineers from the UK and test engineers from Kistler in Germany. In general, I've basically just told it, Kistler basically provided us with vehicle test dynamics on different tracks. And we were basically thinking to give them our machine learning toolbox to figure out how we can do things faster. And so I've got a couple of animations for you to explain in very simple terms of how we approach the problem. In this case, we basically said, cool, let's assume a input is anything that the driver does. My human driver is the input to a machine learning model. And anything that a sensor picks up on the car is an output to the machine learning model. So what I'm basically trying to do is not an AI that creates data for learning and autonomous driving, but an AI that can, after the driver has driven the car for 5 hours, extend the track test virtually by another 10 hours in different scenarios. So when the driver sort of changes the steering angle or changes the acceleration, we get a prediction of the forces on the tires in this example. The most interesting thing is for me that I've worked on system identification, and this technically, if you work in control or in dynamic systems, is pretty much just machine learning-based dynamic systems modeling that for me who've sort of worked with state space equations and stuff like that for years. Even if you're not yet on a page where you think machine learning can transform the way you do testing, I can tell you right now that these models can, especially if you have big test data, blow all other algorithmic methods out of the water. They're quite superior with regard to accuracy and modeling capabilities to anything else I've seen. Obviously, expertise always plays a role in these things, but in general, really powerful stuff. In particular, because the amount of parameters and the complexity of systems that you can model is immense. One really nice feature is that you also need to spend no time doing physical models, and that's not exactly true of Simulink. You get confidence intervals on top of everything, meaning that some people sometimes say machine learning models, it's just pattern recognition. It's good though in testing because if, for instance, I've got a failure, then and this failure has been caused by a pattern that I've never seen before, then the machine learning model will tell me that's why the car didn't work anymore, because I didn't know, like, some sensor was blocked or some of the dynos were out of range. And so this can actually help you debug things. And if you have a little Google about deep learning, then you will see that working with big test data and solving and modeling things really, really quickly, thanks to GPU support and CUDA, is really, really powerful. So quick models, both from a computational and manual point of view. As the next thing, I quickly wanted to dive into the Monolith platform to just show you the results. And there's two things about the results that I think are particularly important. So first of all, this is a dashboard. In the Monolith software, it's a fully no-code environment. You basically go through a notebook workflow where you can sort of build up a solution step by step. And once you're finished, you compile the whole thing into an application that your fellow engineers can use for future problem solving. And what you can see in this dashboard is that the automotive engineer involved in this project pretty much created a dashboard where the different driving maneuvers were here. So if, for instance, like a little bit of a step drive, so the driver goes left, right, then there's maybe a little bit of a more of a slalom, a middle of a sine where they basically had really, really tiny sine sweeps towards the end. So like little jerky movements. And then there's sensors on the car that, for instance, were measured here, accelerations, forces, GPS measurements, and so on and so forth. So when we first looked at this data, we thought, okay, this looks all fine. And this data was supplied to us by Kistler for this case study, assuming that it was all fine. But the first thing we do when we get these data things is normally we build a plausibility model. This means that we have a model that has a rough understanding of the physics, has been trained on a small proportion of the test data, that predicts ahead the rest of the test data. And if you do that, you can quickly see that one of the tests we looked at, and this is basically the neural network, zeroth says, it's happy, it's sort of what it's supposed to be doing. The 10K here means it's completely out of range. And so one of the things that we quickly realized is that for one of the test engineers accidentally swapped Fy and Fz. Not a big mistake, but if you have to figure out why all of your results are off, really painful to do. And so just using machine learning on a very simple way, weak machine learning, just to figure out, have I set this up correctly, is really powerful stuff. Our Kistler friends have told us that there are more than 300 sensors involved. And so reading them all properly and correctly for hours and hours testating is painful. And having a machine learning tool that you can set up within 20 minutes, just proofread whether you've done it all correctly and like point out any mistakes is obviously really useful. So this is the first point. And then the second thing that I quickly wanted to show is here, is that the next thing is that we then basically use 3 tests. 3 generic driving tests and started predicting other tests. Imagine it like that. You're coming to the track test in the morning, and instead of doing an 8-hour day, you work 9 to 11, train your AI, and then everything you wanted to do in the afternoon, you predict. Some German engineers who sort of seen this last week said, oh, cool, didn't quite finish my stuff when they sent me home 6 weeks ago. Can I take the data that I've collected and complement the design space and complete the design space so that I can basically make the decisions that I need to make? Yes, exactly. That's mostly the reason why we did this case study right now and why we made it public. You can continue testing virtually from home. And so I've just put out a couple of examples here where you can see that the basically neural network in the background of this is predicting test results, and it's getting the trends all right. It's not perfect in the sense there's some like sort of environmental impacts on this that it's not capturing. But overall, the automotive engineers involved in this told us that this is good enough to figure out what they wanted to figure out. And then was one really interesting thing, and this is this one. The very last one is a test which is completely different to all of the other tests. And in this test, because it's basically a new test environment that we've never looked at before, the machine learning algorithm is getting the trends mostly right, but it is realizing that there are extreme forces here involved that it's never seen before. And you can see, and this is one of the things that I like about like neural networks that physical models don't do that well, is that it's highlighting the areas that it doesn't know with really big red uncertainty bars. And this just shows you, whoops, this test we actually need to do tomorrow. We can't predict that. The other 2 tests are fine. I can save some money here. Overall outcome of this, if I quickly go back to my presentation, is that once you sort of looked at the first 20% of tests, we could predict more or less the entire remaining one. And the overall number, once we sort of finished this, was that 72% of tests, or 8 out of 11 test days don't need to be done. You can get everything you need from it. And the last thing is that you can automatically identify mistakes in instrumentation labeling, which is also quite handy. As I said before, you don't need to take my word for it. There's a completely public case study. We're currently offering free trials. If you want to basically use the bank holiday to have a look at this, just pop us an email over and you can get to play with this yourself. I want to finish on a high note. The coolest thing we do is working with 3D design data. If you're interested in that, there are a bunch of webinars around on our website that you can read. And if you want to join our private LinkedIn group, we have even more application from controller design, aerodynamics, composite material optimization, high fidelity real-time simulation, generative design, automatic parameterization, manufacturability assessment. We've been doing this for more than 3 years with a lot of industrial partners. There's a lot of cool things that you could try yourself. Thank you.